our data at the Large Hadron Collider. So, Tom, are you connected?
Hi there. Hi.
Hi, yes, I can see you, Tom. Okay, so thank you, Tom. If you'd like to go ahead, and as I say, people, you can ask questions in the chat during the talk, and please keep other longer questions for Tom at the end.
Okay, give me 1 second to try and share. I might need to update a setting. Give me a second, sorry.
In Tom's talk, there's also some really nice Jupyter notebooks. So these are Jupyter notebooks, a nice online platform where you can edit Python code. You might have used some already, and we have some specifically for Atlas. So using Atlas data from Large Hadron Collider, where you can learn to do some physics analysis, some statistical analysis, and learn to do machine learning. So they should be self-driven, self-taught workbooks. Tom will link to them in his talk. And so if you go through any of them and you have any problems or questions, you can always email us and we'll help you through. But we spend a lot of time on Atlas trying to develop these notebooks for you, for students to learn how to do analysis. Oh, Tom is back. Oh, we don't hear you, Tom.
Sorry, there we go. Now, do you see?
Yes, we see your slides.
Full
Lovely.
screen as well.
Yep, full screen.
Perfect. Okay. Hi everyone. So I'm Tom. I'm a senior research fellow at the University of Sussex, and as Kate said, I work on the Atlas experiment at the Large Hadron Collider at CERN. I've been involved in Atlas for a long time now. I did my undergraduate degree actually in theoretical physics, and then I moved to doing experimental particle physics for my PhD, where I was already working on Atlas, particularly on machine learning developments for particle physics analyses. And I'm going to talk to you today about a few interesting examples from our experiment, especially some of the more sort of cutting edge things that are going on that are really quite interesting. So just while this sort of introductory video plays, I'm going to, in this talk, give a basic introduction of what we're looking for as particle physicists, the kind of studies we're doing or what the questions we're trying to answer, including some of the outstanding questions that are things we don't know about yet, and why we're actually doing these experiments at CERN. I'll talk a bit about how we study this physics, so the Large Hadron Collider, what it is and what it does, and specifically then Atlas, the experiment we work on, as an example of sort of a general purpose collider experiment. And then I'll go through sort of a non-exhaustive set of examples of how machine learning is used in the Atlas experiment or in other particle collider experiments as well, to try and analyze the data we get. And then I'll show you some examples of how you can get involved yourself via the Atlas Open Data, and some of the examples there that you can study and have a look at the data for yourselves. So I'll just let this animation finish, and then we'll get straight into it. Okay, so what are we looking for? Really, as particle physicists, our main goal is to try and answer some of key questions, being what are the fundamental particles that make up the universe? So on the left here, you can see what we call the standard model of elementary particles. So these are all of the particles we know about, and then we also try and answer the question of what are the fundamental forces of the universe. So these are how these particles make up everything. And then the idea is to see if we can put this together into a coherent theory to describe how matter and energy work. Looking to do here is to describe how particles interact with each other via these fundamental forces. So we have the matter particles, so these are the quarks and leptons, and then we also have the gauge bosons, which are the how they interact. For each of these fundamental forces, there's a quantum field.
Sorry, you lost your voice for a while. Maybe you can talk a little bit. Everybody in the group, can you hear Thomas?
Hi, can you hear me?
Yes, we hear you now.
Okay, sorry. Let me just switch.
Thanks. Yeah, slightly intermittent connection, but it's not too bad. Tom might change to a different connection.
Oh, can you hear me okay now?
Yes. Yeah, it was just a bit intermittent, Tom, but we could hear you. But yeah, if you
okay, let me try and continue, but let me know if it breaks up again.
Thank you.
Okay. So each of the fundamental forces has a quantum field theory, which precisely describes which particles interact via the force and the gauge bosons and how. So, for example, the electron interacts via the electromagnetic force, which is mediated by a photon, and this is described by the quantum field theory we call quantum electrodynamics. So in reality, actually, what this looks like is quite a complicated equation like this, but don't worry, we're not going to need any of this right now. But it's just to say that we have this very precise theory which allows us to make simulations to predict what we expect to see in our experiments and to try and measure. And then we can also use these theories or develop new theories to try and to predict what other things we could look for that are beyond the standard model. The standard model in general has been a very successful model, although there are still a few gaps and unanswered questions within it. So here's just, well, as the headline ones, I would say there's a selection of them. So the first is, how does gravity fit in? So at the moment, we described gravity through general relativity and generally discussing things at large scales. So not on the scale that we look at these subatomic particles, these fundamental particles. There's no quantum theory of gravity at the moment, mostly because it has issues with what we call renormalization. So this is when you are doing the calculations, you get certain infinities that crop up, which you can't then deal with, which cause issues. If you were to try and developing this quantum theory of gravity, you would need a force carrier, as we have for the other forces. And this hypothetical force carrier is would be a spin to massless, and we refer to it as the graviton. But this would have a very low production rate in our experiments, although we still look for these. It might also be that there are extra dimensions, which is where the graviton essentially sort of hides, or that the sort of extra dimensions are curled up and very small, and that means they're very hard to find. And so that's why it's something we spend time studying as well. Another thing Kate mentioned before, the June experiment. So the June experiment is a specific experiment that studies or will study the neutrinos, which are the least understood of the standard model particles at the moment. They are very hard to detect because of their small interaction rates with other particles. But we do know from experiments from the 90s and 2000s that they oscillate between the different flavors that they have, and therefore they must have mass, which is actually something that's not predicted by the standard model and would also need to be explained. But due to how difficult they are to detect, you need these specific experiments. So actually neutrinos are something which we don't really detect in experiments like ATLAS. We just infer their existence from sort of missing energy and things, but I'll come on to that shortly. So actually most of what we do is not focusing directly on neutrinos, but on other particles which we can detect directly or so more easily. Another big thing is what is dark matter and dark energy? There's a number of astronomical observations of different types that suggest the existence of dark matter and dark energy, which actually are thought to make up the majority of what exists in the universe. But actually we don't know currently what this is, and there's many theories out there, one being for things that are referred to as weakly interacting massive particles, or WIMPs, and these are again something which are searched for, as well as other particles which could explain where this dark matter and dark energy come from. There are also many other particles that we can search for that are beyond, we call them beyond the standard model particles. So there's theories such as supersymmetry, which says for every standard model particle there would be a supersymmetric partner, and this then addresses some problems like wide or the hierarchy of masses that we have in the standard model particles. Or maybe there's other questions like, is the Higgs boson we found the only one, or are there additional ones? And these are all things that we search for with precision measurements at the LHC to try and understand if there are any cracks in the standard model that might explain some of these things. And then another big one is, why is there such a large matter-antimatter asymmetry in the universe? When we describe our particle interactions, we need to conserve various quantum numbers that relate to the particles. And so it's expected that you would have equal amounts of matter and antimatter created. And so in the early universe, there should have been a balance between this matter and antimatter. But actually what we observe now is that there is mostly a matter universe and very little antimatter by comparison. So this is again a big open question. So this is to say that while the standard model is very successful at describing things, there are also these areas where there are still questions that we don't know the answers to. And so it's quite an exciting time, especially with something like the Large Hadron Collider, to be able to try and study and answer these very fundamental questions about how the universe is. So how do we do this? We use this big experiment called the Large Hadron Collider. It sits on the border between France and Switzerland, just outside of Geneva, at CERN, which is the European Organization for Nuclear Research. And you can see it's projected onto the landscape here as this big yellow ring. It's 27 kilometers in circumference, and it's actually 100 meters underground. So it's accessed from various points around the countryside. But for scale, you can see that the lake here is Lake Geneva, which is very large. And then here, actually, just above where it says LHCb, or between LHCb and the ring, this is the runway of Geneva Airport. So for scale, it's actually a very big experiment. In fact, it's the largest in the world, essentially. So it's actually made up of a complex of smaller particle accelerators, with the LHC being the final stage. And each stage accelerates the protons a bit more each time. So it starts from these sort of linear accelerators before going into some circular ones that gradually accelerate the protons to closer and closer to the speed of light. And then at their final energy in the LHC, they're then collided in 4 big general purpose detectors, of which ATLAS is one of them. There's also lots of smaller experiments throughout the different parts of the LHC, the CERN accelerator complex. And these often study specific physics questions or analyses and applications as well, ranging from things like actually developing new accelerator technologies, but also doing things like medical research development and things like that as well. So it's really a very rich environment for all kinds of different experiments going on. It's not just the fundamental the collisions to look at the fundamental particles. There's a lot of additional things going on as well, which is quite exciting. So here's another animation that I'll just let play through, and I'll talk over the top of. So as I say, the proton bunches are injected into the different rings, and they're gradually accelerated up to higher and higher energies. So by the time they get to the super proton synchrotron, which is the second largest, they're of quite a high energy, and then they go into the final ring in two directions, and then these bunches travel through the vacuum tubes as they're accelerated closer and closer to the speed of light, and then eventually, as we'll see in a second, they collide in the experiment. So as they collide, what the experiments do is they essentially take a snapshot of each of these collisions, like a very high detailed photograph, to try and understand what happened. And then we can do various reconstruction and things like that to see what happened in each of these in the detector. So as I say, I'm part of the ATLAS collaboration, which works on the ATLAS experiment. It's one of the largest collaborative efforts ever attempted in science. We are about 3,000 scientific authors in total from over 170 institutes from 40 countries. And a lot of the people that make up this collaboration are doctoral students. There's around 1,200 students, in fact, working on the detector. And they're involved from everything from the detector development, the data collection, so actually running the detector in the control rooms, and then performing the analyses to search for new particles, to study the standard model, and then ultimately we write all these up into papers that to present and to try and understand the nature of the physics. The collaboration isn't just physicists working on the analysis as well. We also depend heavily on the efforts of countless engineers, technicians, and administrative staff as well, who also are vital in making the collaboration and the experiment run. So the experiment itself is the largest volume particle detector ever constructed. It's huge. It weighs about 7,000 tons. And is 44 meters long and 25 meters in diameter. And as I say, it's 100 meters underground in a giant cavern that houses both the detector itself and then a lot of the support things as well. So like computing and power and such as well. And you can see for scale that there are just on the side here, there are some people, and at the bottom. So really to give you this idea that it's huge. And it's made up of all these many different layers that do different things. So as the particles collide, they travel through the different parts of the detector, and depending on what type of particles they are, they interact with different parts. And so, as I say, it's essentially like a digital camera taking a snapshot of each collision, but instead of having your normal number of it's hundreds of millions of channels of readouts. So it's like having hundreds of millions of pixel camera that you can really do a 3D reconstruction of these events. So this is a nice rendering in 3D. We also can look at them from different angles. So we can look down essentially along the detector. So this is looking in the direction that the particles would travel, so into the cylinder of the detector, and then there's sort of a top-down look to see. So again, you can see that there's different aspects that we can take away from these pictures. So again, this is sort of an animation showing how different particles interact. So I will go through these very briefly in a second when it's finished, but it's just to say that there's this sort of layered structure of the detector that means that we can really try and the idea is to try and stop the particles we can, so that we can measure their energies. So each of the parts of the detector here, so we have the tracking in the middle. So this tracks the path of any charged particles. So the entire detector is actually inside a massive magnetic field, and the idea is that by using the magnetic field, we can bend the paths of the charged particles, and then from that we can measure things like their momentum and their energy, and do calculations to work out those things as well. So yeah, the charged particles are measured in or tracked in the inner tracker. We then have the electromagnetic calorimeter, which is used to measure the energies of electrons and photons. And you can see here sort of how these look. So depending on the type of particle, so for instance, an electron we would see in both the tracking part of the detector and the electromagnetic calorimeter. Whereas the photon, the dashed line here represents that we don't see the photon in the tracking, but then we would see it in the electromagnetic calorimeter. Similarly, we then have a hadronic calorimeter, which is for measuring things like protons and neutrons and anything that is made up of quarks and gluons. So we refer to these sort of sprays of particles that happen when they interact in the hadronic calorimeter as jets. And this is a sort of one of the key things that happens a lot of the time is you get these, because we're colliding protons, which are made up of quarks, these then recombine when they've collided with other quarks to give you these various different sort of hadronic jets that we see. And then finally, on the outside, we have the muon spectrometers. So muons are like the heavier cousin of the electron, but they don't interact in the same way. They usually have a lot more energy than the electron, and so they pass through all of the detector, and we can't actually stop them in the same way we do the other particles. So actually, we then measure them in all of the sections of the detector, and from that we can reconstruct the paths back to, again, work out things like the energy and the momentum, and identify them as muons as well. And then, as I said earlier, the neutrinos we can't actually measure, so these pass through the detector without being stopped and essentially are invisible to the detector. But because we know the energy of the protons being collided, and the fact that we initially have nothing in the detector, we can essentially sum up all of the particles we do see and all of the energy there as a vector sum, and then from that we can work out what missing energy we have. So we call this the missing transverse energy, and that's where we infer the presence of invisible particles that we didn't measure, like the neutrino as well. So that's a bit of a whistle-stop tour. I don't expect everyone to have taken it in. It's just to sort of say some of the inputs then that will be relevant to some of the machine learning things later, so that you have an idea of the kind of things we're looking at and what we're measuring. So alongside the detector, we also make a very heavy usage of the worldwide LHC computing grid. It provides computing resources to all of the experiments and to other experiments outside of particle physics as well, to provide sort of an unprecedented amount of resource to both analyze data, to store it, because we're generating an incredible amount. I've got some figures in a minute. And also to distribute it throughout the world so that people all over the world can access it as well. In total, it's about 1.4 million computing cores. So as I say, it's really a phenomenally large resource, and it consists of about 1.5 exabytes of storage, as I say, across many different sites in many different countries. In total, it's running about 2 million tasks per day, and it's used by something like 12,000 physicists around the world. And it's really vital, as I say, and without it, we couldn't do the sort of computing we need to analyze the amount of data that we have, and to also produce the simulations that we use to analyze it as well. So moving on to the machine learning side of things, I put this here because I thought it was an interesting plot. So there's a group called the Inter-Experimental Machine Learning Working Group, and I've linked their GitHub here, and they keep a living review of the different machine learning papers that are published in high energy physics. And as part of it, they make this plot which shows the interest, or essentially the number of machine learning papers in high energy physics per year. And you can really see that there's been big growth in the last sort of decade of the interest in machine learning. I should say that machine learning has been adopted in particle physics for quite a long time, but really with the advent of sort of the more modern GPU-based machine learning applications, we've really benefited in what we do. And that's why there's been such this sort of massive growth in the number of papers published. And it's not just for analyses, there's also the development of new techniques that are either specific to particle physics, but also can be applied to other things as well. As well as actually the machine learning for analyses. There's also things like publications to do with how we generate our events as well for the simulation, and also things to do with theory as well. So a sort of a snapshot of what the analysis workflow looks like in terms of what we do. So we do these collisions in the accelerator. There's something like 40 million collisions per second. We then have to reduce this down by quite a lot by looking for interesting characteristics using what we refer to as triggers. And this is something of the order of 100 to 1,000 a second. We then have to do some particle reconstructions, calibrations, selection of events for looking for the specific signals and reducing the background. And then finally, we do the analyses. And machine learning is pretty much nowadays used in all aspects of this. So we use it in the triggers, we use it in the reconstruction, we also use it in the analysis. So it's really sort of prevalent throughout the whole analysis chain. And as I say, it's a very important thing of aspect of what we do. So I mentioned trigger systems, just to say that, just to again give you some idea of the sort of vast data that we're dealing with. It actually works out that there's something like 1.7 billion collisions each second in the LHC or in Atlas, and this is corresponds to a combined data volume of more than 60 million megabytes per second. So this amount of data really is way too much for us to deal with. We couldn't write it to storage fast enough, and so we have to essentially select an amount of data that's manageable for us to then process. So essentially, the trigger system is designed to select from these millions and billions of collisions, and then to select for interesting events with characteristics that we want to study, and get it down to about 1,000 of these. And it has to make these decisions very fast. It's in about 2.5 microseconds per event. It has to actually decide whether or not we keep each of these events. The data is then taken. This is done by taking the data from the different parts of the detector channels directly, and then it's these decisions are made, and then it's written to storage. And I won't go through an example right now, but it's certainly something which is very much studied and is being developed for the future. For Atlas is to incorporate machine learning into the trigger using things like GPUs, so graphics cards, or also field programmable gate arrays, to really try and incorporate machine learning in, so that we can, as I say, we need to make these decisions quickly, but with machine learning, we can try and make more complex decisions in the short time than we would otherwise be able to make. This is actually already deployed in experiments like LHCb. They already use GPU triggers directly to select from their data. And as I say, it's something that Atlas is working on developing as well for the future. So one of the main aspects of machine learning that we use in analysis is classification. I believe you've been going through various tutorials about different methods, and the reason we use it is because we are looking often for very rare events, signal events in very large backgrounds. The signals can also have very similar signatures and final states. So what I mean by that is the types of particles and decays that we expect, and the sort of kinematics and characteristics. So that's what I refer to as the signature, look very similar between the signal and the background. So we really need to try and disentangle these two things. As I say, classification is probably one of the most common uses of machine learning and analyses. This has been used right the way through, as I say, for more than even a decade, for even longer. And the idea is it goes beyond the simple cut-based analysis. So I've got an illustration of actually from one of the workbooks from later of a cut-based analysis, and how we then would apply cuts to make a decision about whether we think an event is signal or background. So what we can do with the machine learning is, rather than doing this sort of cut flow, we can use the input variables from this and other reconstructed variables and sort of high-level information to input to the machine learning, which can then exploit sort of higher dimensional correlations and relations between the different data points to try and, or between the different variables to try and separate these signal from background. Lots of different types have been used in the past, and one of the things I worked on for my PhD was using support vector machines. Boosted decision trees, like there's a decision tree example here at the bottom left of sort of how it would look in 2D, have always been very popular. But now really, I think one of the main things that's being used is neural networks. People are very experienced now using neural networks, and the ways that they're being developed and used, we can get a lot out of them. And then I just put one here as well that it's a very old plot now, and it's outdated, and the analysis has been superseded. But this is actually one from my PhD thesis that was looking at using a BDT to look for the production of 2 Higgs bosons at a time. But I just think, yeah, it's a nice illustration of how you can have the signal, which is in red, being separated from the very large background, which is in the different colored filled histograms. Okay, so now on to a slightly more, I would say, interesting, novel application of machine learning. So for these ones, there's some nice briefings that relate to the papers that these are from the Atlas experiment. I haven't necessarily worked on these directly myself, but the algorithms and the things that are used by so many people throughout the experiment that I think they're really worth sort of noting as new ideas, which are worth reading about, because they're as I say, novel applications. So the first thing is transformers for jet flavor tagging. So one of the most common things that we get produced in the proton-proton collisions are these particle jets, the sprays of hadrons that I mentioned before, that are created when quarks and gluons interact with each other in the detector and then combine to make hadrons. And so we call these jets, and essentially it's because we identify all the internal components and make them into these sort of cone shapes to identify where things have traveled and where they're connected to each other. These jets really dominate the data we collect. We need to identify what type or flavor, as we refer to it, of the quark that initiated the jet is, in order to try and understand the process that generated them. But this is actually a really challenging thing. There's lots of additional information to do with the tracks that we get from the detector, where the tracks are connected to different vertices and things like that, and then how we try and we then do these reconstruction techniques to make the jets. It makes it quite hard to understand what the original quark is that was then related to the jet. But this is really a crucial part of the analyses, because we need to know what they were in order to reconstruct the particles they came from, to try and do the precise measurements of the standard model we want to do, or to search for new physics. So Atlas has recently deployed this new method, which is called GN2, which is a new flavor tagging algorithm using these transformers. which are essentially a type of neural network that has access to a lot of the information that we have from the detector, so things like the tracks and the track energies and locations and things like that. And it uses some algorithms that allow it to be sort of permutation independent, so it doesn't matter which order you supply the information in, and you then combine some of these things, and you can then put it into the transformer, and it can then give you a very good idea of what quark the jet originated from. And one of the benefits of this is, compared to the previous algorithms, is that there were lots of intermediate sub-algorithms that needed to be developed and crafted to then try and do some of this, to gain some of this information that then would then give us the output, which we could then use to try and determine the flavor of the jets. But with this new method, with these the special sort of architecture of the neural network, it then eliminates this. So it really allows us to the algorithm to pick up on the underlying information to try and identify these jets. As I say, the primary goal is to predict the flavor of a jet, but it can actually go beyond this, and you can incorporate auxiliary objectives into the training that allow you to try and identify more of the underlying process that generated. This both enhances the model's overall performance in terms of the flavor tagging, but it can then also provide deeper insight into the actual physics signatures that it's learned, and where it may need, more developing or improving. However, it's already leaps and bounds ahead of the predecessor, which is referred to as DL1 in various. There's DL1, DL1R, and DL1D, but DL1. It's something like 3 times better for the certain types of jets between other types of jets. And in one of the more recent measurements of di-Higgs production, so where you have 2 Higgs produced at once, it improved improved the measurement by over 20%. So it's a very promising method, and I think we'll see there's still some ongoing development for it, but I think we'll see a lot of interesting physics results coming because of the improvements in this sort of transformer technology for not just jet flavor tagging, but it can be used for other applications as well to try and identify the origins or the underlying processes of particles more from the sort of raw detector information, rather than some of the, as I say, the intermediate reconstruction we would otherwise do. So the next thing I want to mention are graph neural networks for reconstruction. So the idea that we want to do with a graph neural network is to try and reconstruct heavier particles from the lighter particles that the heavier particle decayed into. And we do this with these sort of the graph neural networks. There's a link to some slides that go into more detail about how these are constructed and trained. But the idea is essentially all of your reconstructed objects. So these are things like jets or the leptons, so electrons and muons, in your detector are represented by these nodes, which are in this sort of cartoon up here in green. The edges are bidirectional and connect all pairs of reconstructed objects. So essentially, if this is an electron and this is a jet, the edges represent how like distances in the detector or differences in energy between the various things. And then you can also add global features, which are things like the total number of jets or the total energy. So things that aren't specific to an object, so like to a particle, but are just sort of general information. And then what happens is, by constructing this graph, you can you train the neural network to predict the identity of edges, or at least edges which are in particles that are related to each other. So for instance, it's used in this analysis, which I have linked here, which is the search for or the observation of the four tops process, which is an extremely rare process in where you have four top quarks produced together, which are the heaviest of the quarks. And what it does is it identifies where, for instance, these are two sets of three jets, where it has identified that these are the decay products of one of the top quarks, and then the blue ones are the decay of the other, and then there's other particles within the event as well. But it's trying to identify where the things are related to each other. And then by using this, so it identifies where it thinks the particles are from, and then from that you can either reconstruct the particle candidates, or you can even just use the score. So that's what's done in the analysis to separate between, for instance, the four tops process, which is in red, and the other background processes as well. And so you can see that similar to other applications where you're sort of doing classification, you can use it again to separate between the signal and background. But I think this is the graph neural networks is a very interesting way of trying to do these reconstructions, and there's a lot of work going on using these as well at the moment. So I think the final example that I will show just now is for anomaly detection. So this is an unsupervised machine learning technique. So a lot of the things I referred to previously are using supervised machine learning, where you have labeled data, where we use our simulations that we run from the theory to train the neural network. So we have our labeled simulations, so we can say, okay, this is a signal event or this is a background event. And then what we do is we train that, and then we apply it to data and we compare the outputs. In unsupervised machine learning, you don't have the labels, you're just giving it essentially the data. And so this allows us to do a new style of analyses, which doesn't have any preference for a type of model, because you're not training it on something that's labeled. You're just giving it the data. It doesn't have any expectation of what it should be seeing or what it's expecting. So what was done for this analysis is it used a complex neural network with millions of interconnections between each of the nodes in the network, that's trained on real data, and it sort of applies convolution and then unapplies it to try and look for or be trained to see what it expects to be as a typical LHC collision event. And then filter those ones out, and then leave behind things which are unrecognized or atypical collision events. So you're really looking for something, you're essentially trying to train the method to find something which doesn't look like the normal thing. And by that, you can then look for these large differences in the events, which are the things labeled as the anomalies, which the algorithm has trouble identifying, or thinks it has trouble identifying. And then the chances are that these might belong to a new physics phenomena, or a new particle or something like that. So what you can do is you can filter out all the events that look like what it expects, look at just the ones that remain that are the anomalous events, and then try and do things like reconstruct the invariant masses of the particles, or look at other kinematics to do with the particles to try and see if they're described by a standard model process or not. So on the left here, you can see the black points here are the actual data, and then there's a few different models here, and so essentially, like, the majority of events are in this very low loss, which is you're basically looking for things where the loss is larger, because it's having trouble identifying them then. But you can see that the majority of the data is down here, and then some of these models then have the loss starts to become larger. But there's actually, this is from the paper as well, there's these are much more extreme examples where you can see that really, if you set certain benchmark models to test how it looks, you can see that there really then is a big separation between the majority of the data, and then, so these ones are actually simulations as well, but what you would expect if you were to see something new. So this is essentially where you're looking for the anomalies. And then the plot on the right shows from the paper one of the most significant bumps, which is just this point here. So these are events which were identified as being anomalous, but then, as I say, what you do is you take the anomalous events, you reconstruct the masses. So in this case, it's a jet and a muon. You add them together to get their mass, and then you look to see if it's modelled by your data. And in general, it fits very well to sort of your expectation. There's this one bump here, but it actually isn't particularly significant and is actually probably just a statistical fluctuation. But just to say that there are, ongoing things looking at these certain things to try and identify where to look for new physics without putting in a specific model. So I think this is also a very promising area as well. This is also something that you could deploy in something like your trigger, so that you're not, again, adding expectations of what the events look like in your trigger, but you are able to sort of look for anything that looks unusual and then try and then analyze it after the fact to see whether or not it is unusual or if it's just a statistical fluctuation. So just a word on, so these are all things that are ongoing at the moment. We've got about another year of running of the Large Hadron Collider before we go into what we call a long shutdown, where we're doing a lot of upgrades for what we then call the high luminosity LHC. So at the moment we're here in 2025. Long shutdown 3 is where we will turn off the LHC and do a lot of upgrades to experiments. But then the red points here really indicate the intensity with which we're colliding the protons, and we're going to, after the shutdown, we will really increase this intensity, which is why it's referred to as the high luminosity LHC. But with this, it will bring a huge increase in the amount of data, which also poses a significant challenge. So, for example, this plot at the left bottom is of a simulation of an event that we would expect at the high luminosity LHC, where there's 200 particles colliding in the detector at once, and then you sort of have to try and disentangle all of these tracks from each other to work out which particles were related to which collision and what happened. So it's really a big challenge for the kind of analysis we need to do, especially in these dense environments. And you can see on the bottom right, there's a plot of sort of the wall time, so the time taken to analyze an event as a function of the number of collisions that are happening in the detector. So as the number of collisions increases, it sort of exponentially goes up, and so this really poses a challenge. And so machine learning will really be key in our ability to process the amount of data we get, just not only at the detector level, but then downstream of that as well. Okay, so the last couple of minutes I'm going to mention about Atlas Open Data. So we've actually just done a new Atlas Open Data release. So the idea of this is Atlas is, as an experiment and a collaboration, is dedicated to releasing our data to the public, to people to analyze and to have a look at and have a go themselves. And in order to do that, we also release related software and tools and educational toolkits as well that really can give you the opportunity to have a go yourself. So as I say, we've just done a new release. In fact, because there's before we just had Atlas Open Data for education, but we also have Atlas Open Data for research. The research open data is essentially one of the one of the formats that we actually use internally within the experiment, and it's and what we've released is 65 terabytes of simulation and also real physics collision data for people to analyze. The education version is derived from the same set of samples, but then it's just a simplified format to get people started quicker. But actually, it's completely transformable between the two. So if you start with the education, you could go to the research or vice versa. And so it really gives you the opportunity to have a go if you want to try out some, analysis techniques or to do a bit of machine learning or things like that. These data sets are really easy to use, and they contain, as I say, millions of proton-proton collision events, and there's lots of different physics objects, but it's all very it's all very nicely detailed with examples and documentation, and also like Jupyter notebooks that you can work through as well. And as I say, they're linked in these slides, which I'll make available as well. There's a few workbooks I wanted to highlight. Unfortunately, at the moment, because we've just released a new set of data, we're currently working on updating them. So they're sort of a work in progress at the moment. So they're not currently fully functional, but hopefully we'll be back in the very near future. But I wanted to just highlight that there's, firstly, there's one that is on a search for dark matter. So this takes you through how to do an analysis of looking for dark matter using neural networks and boosted decision trees, but also through some of the machine learning aspects as well. So how the machine learning works to do this. And then there's another nice one, which particularly now with the new, once we've got it up and running with the new version, is to a notebook which lets you rediscover the Higgs boson yourself with a neural network. So the plot at the top is actually from the standard analysis, which is also, there's a workbook for, which is linked from the first one. But you can also then build upon doing the standard analysis to also train it with neural networks to try and analyze it as well. So you really have the opportunity to have a go and, as I say, rediscover the Higgs yourself following these notebooks. The last thing I want to highlight is our new ML visualization dashboard. So this lets you explore sort of interactively some of the data. So there's things like at the top left here, there's distributions where you can look in 2 dimensions at various different variables of the simulation and the data broken down by the types, and then you can sort of apply different filters and have a look yourself. You can then apply a neural network to see how that would use the inputs, and you can select which inputs you want and different like architectures, so number of hidden layers, number of nodes, and you can really sort of play around and configure it and see how it affects things, and then you can see how the output looks and how you can then use the output to try and increase the significance to search for the dark matter. So I won't go through the summary, but yeah, thank you for listening, and hopefully you can see that it's an exciting time for the Large Hadron Collider and collider physics in general, and that we make really heavy use of machine learning throughout the experiments for many different applications. And as I say, this is just a sort of illustrative example, a few examples. There's many more out there to explore, and there's lots of really interesting work going on in the community. And finally, there's the Atlas Open Data, which is available to everyone and provides many exciting examples that allows you to have a go yourself and to yeah, to look at the physics data and to do some machine learning as well. So yeah, thanks for listening, and I'm happy to answer any questions.
Hi, Tom. Thank you so much. That was absolutely wonderful talk. It was really interesting to hear about all the different things Atlas are doing with machine learning. So let's start with some questions. Please put your questions into the chat. Ask anything you'd like at all. So I can see there's a question from Carl. So Tom, the question is, how much affected are you if the machine learning model misclassifies, and do you do anything about that? Thank you, Carl.
Yeah, so it's a really good question. So a lot of the development in what we do is to try and understand, essentially is to understand exactly that point of like how things might be misclassified or where we might miss information. All of these things are calibrated to different working points essentially, and so then we optimize for each analysis. We'll use different working points, and then so we can use the simulation to try and understand where we might have data losses, or not data losses, but like where there might be inefficiencies or things that we need to account for, and that's where we sort of then can either calibrate it to adjust for that or optimize it to try and to look for the different things. One of the challenges is because there's such a rich set of analyses going on in Atlas, it's hard to calibrate it for everything to make it perfect for everything. Yeah, there are inefficiencies occasionally, but of course, with the vast amount of data we have, and it's all very statistical anyway, it's all taken into account through as I say, the calibrations and things like that.
Perfect, thanks, Tom. Yes, there's another question from Layla. So the question asks, how can we be sure that an event flagged as an anomaly by machine learning is not just due to detector noise or imperfections?
So again, a really good question. We don't. Because everything is very much a statistical process, we have to look at many different examples. So a single example wouldn't necessarily tell us that, okay, this thing is definitely an anomaly. What we would do is we would look at a series of things that had similar characteristics, and then from that we can try and determine if it really is something new or some new physics, or whether it's just, as you say, like some detector noise or a statistical fluctuation or things like that. So it's the idea of the anomaly detection, as I say, is to flag things which could be interesting, and then once we flag them, we can then do a more intense study of those specific events. But again, it's not any single event. It would be a series of events to try and statistically understand, yeah, if there was something significant rather than, as you say, yeah, some detector issue or what have you.
Yeah, sorry. Thanks, Tom. I was muted. Yeah, I wanted to ask actually, so with high luminosity LHC, so the next iteration of the Large Hadron Collider, which will turn on in a few years, I think you were saying that there would be a lot more interactions every second, and we're going to leave machine learning more and more. I mean, how is it going to be more possible to detect some of the rarer processes like dark matter or any other types of new physics, and how do you think machine learning is going to help us actually find finally this new physics?
Yeah, so I mean, the answer is yes. The hope is that we can really probe into either really precisely measuring standard model processes to look where the standard model might start to break down, or we can look for really rare new things. The data is going to be really like an order of magnitude bigger. We already have billions of events, but it'll be even more events. And so the challenge will be analyzing that amount of data. As I say, firstly, the challenge is recording the data from the trigger, because the actual interactions or the collisions in the detectors will be an order of magnitude more. So machine learning, that's why I say in the triggers, is something that's very heavily being worked on for the high linear LHC upgrade, because we'll really need to be able to make these quick decisions about what we think are interesting events and what we want to store. And then downstream of that, machine learning will be very important, because we'll have this order of magnitude more data in order to be able to analyze it, to look for these rare things. But because we have more data, we can also really probe the corners of the phase space that we might not have previously been able to look at because we didn't have the statistics.
Okay, so gives us a strong possibility to maybe look for new physics. Thanks, Tom. I see Baktash, your hand is up. Please go ahead.
Hi everyone. Thanks a lot, Thomas, for the very nice, excellent talk. I have a question on the negative weights in particle physics, because in particle physics, when we produce samples, Monte Carlo samples, we usually have negative weights.
Yes.
And it's usually problematic, I think. And I want to have your 2 cents on this. What's the correct way to, should we kind of exclude these events with negative weights, or how should we deal with this? And also, what is the correct way?
So I don't have a single answer as to what is the correct way. They are an issue, but they are part of because of how we simulate our do our simulation, we end up with these negative weights. They technically need to be used because without them, you wouldn't get the correct distributions overall. There's various treatments that people do. I think in general, what's done is it's on a case-by-case basis of an analysis as to see the impact of the weights, because some of the processes, depending on what you're simulating, will have a bigger fraction of negative weights than others. So it can be more or less important. In some cases, you might simply be able to just, as you say, drop events with negative weights, provided you have large enough statistics in general. Sometimes you can renormalize the weights, like overall, to account for the fact that you're subtracting the negative weights to give you the correct distribution. But as I say, there's no real single answer. It's really on a case-by-case basis. In general, the ideal thing is to generate more and more statistics, so you don't necessarily need the negative weights, but obviously we're limited in those resources as well.
Okay, thanks. I just want to make sure that my understanding is correct in this regard. So if we have larger amount of events with negative weights, this will impact the value of loss function, I guess, right?
Yes, yeah.
Okay.
So the other thing that I think some people have done previously as well is to construct a different loss function that is less sensitive or takes into account the fact that you have negative weights as well. It's just that the standard loss functions you get often won't account for the negative weights, or it does the wrong thing essentially in the calculation when you add the negative weights in.
Yeah, great. Thanks.
Thanks, Tom. Thanks, Vaktash, for the interesting question. Okay, so I think let's thank Tom again for a really interesting talk. Any follow-on questions, yes, do get in touch. And we'll take a break now before the next talk, which will be from Professor Stephen Sargent, who will be talking about machine learning, looking at how it's used along with AI in astronomy. So thanks a lot, Tom.
Thank you, everyone. Have a good day.
Thanks.